Hello, hello, yeah, what? Hello, 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 hello. What the fuck is going on? Hello? Test mic check. 1, 2, 3, 4. Mic check. Mic check. 1, 2, 3, 4. Mic check. Something's wrong with my mic again. What the fuck? What the hell happened? I did nothing to this thing yesterday. Test 1, 2, 3, 4. It's not that. What the heck happened? What the fuck? Hello, hello, hello. Hello, hello, hello. What the hell is going on with my microphone now? 1, 2, 3. 1, 2, 3, 1, 2, 3. Huh? My mic is fucking dead. One, two, three. 1, 2, 3. Hello, 1, 2, 3. What the hell happened? Something happened to my mic. Unfucking believable. 1, 2, 3. 1, 2, 3. 1, 2, 3. I wonder if it's the mixer. What the fuck? 1, 1, 1, 1. 1, 1, 1, 1, 1. The mic is fucking dead. Huh. Well, the output there goes into here. There's something wrong. Oh, what a beautiful start to the day, huh? Test 1, 2, 3, 4. 1, 2, 3, 4. Wait just a minute. 1, 2, 3, 4. 1, 2, 1, 2, 3. Huh. Lovely. Why am I having this problem? Why am I having this problem? Well, I'm gonna have to change the mixer channel. I don't know what the fuck is going on. Test 1, 2, 3, 4. Wow, hello? I got another piece of equipment that I use. And two, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2. Test 1 2 3 4 4 3 2 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. I may have a problem with this other device that I use. Why? 1 2 3 4 1 2 3 4 1 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 1 1 1 1 1 1 1 1 1 1 whoops 1 1 1 1 1 1 1 1 1 1 1 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. I wonder if the preamp died in this other mixer. 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. I'm cranking this thing like crazy. 1 2 3 4 1 2. Now I'm overdriving. 1 2 3 4 1 2 3 4 1 2 3 4. It's still something's not right. Something died. Hello, 1 2 3 4. It sounds like it's overdriving. Wait. 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 1 2 3. That's the echo I use there. 1 2 3 4. Hello, hello, hello. I cannot believe this. It sounds dead. Wait, there might be another problem here. But I recorded it and it didn't sound good. One, two, three, four. Hang on just a second here. Let me try something else. I don't know what's happening. I think 1 2 3 4 1. Oh, well, it was still low. This damn mic here. 1 2 3 4 1 2 3 4 1 2 3 1 1 2 3. Oh, so that does make a difference. 1 2 3 4 4 3 2 1. I can't believe the input on this other effects processor has to be cranked so high. 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3. Hello, Dolly. Oh, hello, Dolly. Oh, jeez, in Christmas. Damn fucking white cable. I think we're getting it fixed. Part of the problem was my audio mixer sound is a little bit low. What's going on here? 1 2 3 4. We're getting there, I think. I don't know about the background noise. I gotta do another mic test here. Back this up now. I don't like the microphone right in my face. Now that seems a little bit low. Let's crank it back a little. Hello, hello, 1 2. Alright, let's see here. Where's my recorder? 1, 2, 3, 1, 2, 3, 3. Mic check, mic check. Mic check with music. Mic check with music. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. Alright, bear with me for just a second here. Sorry about live testing on stream. 1, 2, 3, 3. Mic check, mic check. Mic check with music. Mic check with music. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. Well, it's still a little bit low. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. Okay. I don't like being that forward into the mic. I guess that's gotta be where it is, right there. Yeah. What am I playing? Oh yeah. It's this game. Wait just a minute. Am I actually streaming it? Nope. Where am I? Game capture. So we're gonna take a couple hours maybe. Let's see. Let me just edit my. Twitch is messing up with my. Oh my god! Wait just a minute. That's not right because I just changed this over here. It's not saving the correct name of the stream when I in my stream list for some reason. I put part 1. What the fuck? Constant cold temperature, creative mode, realism, and the gas laws. I put something else in here and it didn't take. Maybe I forgot to save it. Oh wait, this is actually part 2. Every time I save it, it never seems to register and I have to go back to the video list and re-edit it. Twitch doesn't like me anymore because I'm just that good, I guess. What's the matter with you? Eat your piece of corn here. Look, what's this piece of corn? Eat that corn. Yeah, eat that corn. Come on. Eat the corn. Don't eat my finger. The corn right there. See it? No, not my finger. What are you doing? Kissing me. Kiss the bird already. Kiss the birdie. Kiss the birdie. What? Kiss the birdie. Yeah, kiss the birdie. What? Can you do it? I gotta get a parrot cam one of these days. What? Alright, so I did some other stuff earlier and I gotta put this away. Somewhere. I got so much stuff here. I really wanted to get into more of, don't you take a shower now on my paperwork, okay? So theoretically, we calculated the volume of a pipe cylinder to be 200 cubic inches. But our temperatures are not stable, so that's what we're doing in creative right now. I made a typical looking base that I plan on building. And so we're trying to, I haven't actually, I think there's a pressure problem up here. No, wait, is there? No, I think it's working. Let me see, it should be working. It's just taking forever to... Whoa. What? Wait. What did I do here? Oh, this is the bottom room. So this one seems to be working.
Light on.
Where is everything? I'm probably gonna need a CO2 filter. You know, maybe what I should do is I should work on an airlock, learning the airlock business. I'm not into the airlock business. So the room where that can is located is pressurized. Oh, that's a problem. Because it needs to be... The temperature of the pipe coming out of the oxygen is the temperature of the oxygen in the tank. And it settles to room temperature. And the temperature of that pipe, I wanted the temperature of the oxygen to be low, but now I'm realizing that the temperature is going... I may have to look into these radiators and figure out what they're all about. It's setting the... It's putting that temperature in the room of the air that I'm trying to regulate. And then I was thinking, I had an epiphany. I was thinking I could use pipes to control the temperature of the room. So if I control the temperature of where the tank was located, I mean, theoretically, then I could have the tank in the room. But why would you want an oxygen tank sitting in your living space? It doesn't make any sense. And this room here is supposedly the hot room where I'm keeping other chemicals. And their temperatures... Their temperatures may be different depending on the chemical. Just out of curiosity. Well, now see, there's no way to delete these, is there? Yeah, there is. Yeah, there is. I have an idea. I like this game because I keep coming up with these ideas. I have the idea. I can't delete the component. However, I can clear what's in the tank. Oh, that's not going to work either because then I'm going to have piles and piles of tanks up there. Maybe I just have to bring the tanks in here and throw them out. Shut it, bird, like this one here. Oh, that seems to be a good tank. Oh, wait a minute, that's oxygen? So my question is, why am I not getting pressure up there? I have to figure this out. It's a little bit of a disaster. Alright, let's just go up there. I should have another way of getting up there besides using this jetpack.
Jetpack on.
Use a slow elevator or something. Or actually... Well, see, it needs to be... Actually, no, it doesn't. I could have put the room next to my living quarters, or like in the back instead of up top. Because the idea is to keep the oxygen tank. That would apply to all the other chemicals. To keep them, I'm having this weird epiphany thing. If I had all the other tanks in a separate room, I gotta go find something out. I gotta go outside and figure something out here. So when we got the oxygen, it came in at 20 degrees.
Jetpack on.
So what we're gonna do here, I don't think anything's gonna explode with the temperatures that we're using. I just don't want them to roll towards the ship. Oh. Let's see if we can find dynamic gas canister. There's 2 of these. That looks like a small one. I wonder, those are filters. Let's see what this top one looks like here. That's a portable tank. And its temperature's 20 degrees. Okay. Oh crap, I didn't want to make another one. Well, I did, didn't I? Because I just like nitrogen. Now we're gonna look up, let's look up oxygen. See, I only got one of those. That's 20 degrees. That's the same number of moles. Let's see what else we got here. Let me go back to this nitrogen, because I want to find out what this is. Oh, that's nitrous oxide, okay. It's 20 degrees. Dynamic gas canister, air. That has a mix. We could, let's see, let's write this down here. Air mix. So we've got N2, 75%, 1,900 moles. And we've got O2, 25%, 625 moles. Air, we've got some CO2. Let's see what else we got here. There's an empty one. We've got fuel. Fuel mix is H2, 75%. Hey! Stop farting around with the paper over there, shitbox. 1,900 moles O2 25%. 625 mole. So if we add that up, we get 2,520. 2,525, which is 25 more moles more than 2,500, which the other singular cans are. Not that that really matters too much. Alright, what do we got? We got fuel, nitrogen, nitrous oxide, oxygen. We've got pollutants. Don't tip over. Pollutants is X. I'll tell you why I'm doing this later. Well, I don't need to write that down. Well, for one thing, a stationeer is smart, and he's always supposed to know everything that's in his product, as it were. Rocket fuel. I probably don't even need to write this down. H2, 67%. 1,000 moles. O2, 33%. 825 mole. Oh, wait just a second. Okay, I just remembered something else rather interesting that I probably should have made note of. What else we got? We got volatiles. There's water, volatiles. I guess oxide. I don't think oxide comes in that. Volatiles does. Wait a minute, oxide. Okay, never mind. Let's just put this one in here. Okay, so, well, that doesn't really matter. I mean, the temperature, the pressure that they're giving me is 7.71 at 20 degrees. But the tanks, you can have like up to 10,000 before they explode or something. Who knows? Volatiles is H2. And water. Don't tip over. No, come on. Just. No, don't tip. Oh, well, I just made it tip over because I'm. Water, we got H2O. So, theoretically, I mean, I don't know for sure. Let's see, the law says that, where I have to write it down because I can't remember. I don't really understand it, but at any given temperature or pressure, 1 mole of gas will occupy a fixed volume regardless of gas. Or something to that effect. My mind is not very logically oriented. It's very difficult for me to understand logic. I'm more of digging too deep into things to try to figure things out. Now, there's also what's called standard temperature pressure. And there's actually two different standards. What is that temperature? What was that? Alright, so they're using centigrade. I finally, whoops, I finally think I found a conversion formula that uses Kelvin for the gas law. Where did I write it down here? Be good. Let's see. There's a constant, and there's another number that they use. Well, let's look this number up. Or rather, the constant here. I think it's the constant is a number that is the same for all gases at a given at standard temperature and pressure. However, I'm not 100% sure, so let's just see what it says here. What? Oh my God in heaven, why? Alright, so the Rankin scale is a thermodynamic absolute temperature scale. Like centigrade's absolute, I think. Or whatever, no. Absolute 0 is Kelvin. Minus 273.5 degrees, which theoretically, you can't create a temperature below that. It's based around absolute 0. Rankin is similar to the Kelvin scale in that it starts at absolute 0. 0 degrees RA is the same as 0 K. Why do they have two temperatures? I may have done something wrong. Alright, let me look up this again. Ideal gas law. And there's something else that we should look up, but I don't have a scientific calculator. So the ideal gas law states that PV equals nRT, where P is pressure, V is volume, and T is temperature. Then you have N and R. N is the amount of substance. In chemistry, the amount of substance in a given sample of matter is defined as the number of discrete atomic scale particles in it divided by the Avogadro constant. In a truly atomistic view, the amount of substance is simply the number of particles that constitute that substance. Particles or entities may be molecules, atoms, ions, electrons, etc., depending on the context. The value of the Avogadro constant is defined as 6.022, etc., times 10 to the 23 mol minus 1. What is in a truly atomistic view, 1 mole equals 6 point, etc., times 10 to the 23 particles. Wow, that's a big ass number for 1 mole. That tells you how small these molecules are. I'm going to just jump to this Avogadro number. And therefore the conversion constant is simply Na equals 1. The amount of substance is sometimes referred to as the chemical amount. The mole, which is not a rat, except for me, is the unit amount of substance in the International System of Units. Defined since 2019 by fixing the Avogadro Constant at a given value, etc., etc., etc. Historically, the mole was defined as the amount of substance in 12 grams of carbon-12 isotope, etc., etc., etc. As a consequence, the mass of 1 mole of a compound in grams is numerically equal, for all practical purposes, to the mass of 1 molecule of the compound. In Daltons, the molar mass of an isotope in grams per mole is equal to the mass number. That is on your periodic table. For example, a molecule of water has a mass of about, okay, well, they're going into a different, something else there. We need to get into that. Law of multiple proportions. It is often much more convenient to work with amounts of substances, that is, the number of moles or of molecules, than with the masses, grams, or volumes, liters. For example, 1 molecule of oxygen, O2, will react with 2 molecules of hydrogen, H2, to make water, H2O. So if you look at the chemical bond, it takes there. Wait a minute. Yeah, there's 1 mole of O2 will react with 2 moles of H2. It's a little bit complicated. The same chemical fact expressed in terms of mass would be 32 grams of oxygen will react with approximately 2 grams of hydrogen to make approximately 18 grams of water. And the numbers would depend on the isotopic composition of the reagents. Blah, 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 blah. In concentrations of reagents and products in solution are often specified in moles per liter rather than grams per liter. I'm just reading this here. I don't want to get too complicated. Let's see. Size like water. Ratio is the molar mass. Amount of concentration. There's something else there. Alright. It looks like there's one other thing here. So we have molar heat capacity. Molar heat capacity of a chemical substance is the amount of energy that must be added in the form of heat to 1 mole of the substance in order to cause an increase of 1 unit in its temperature. So, you see, I think the moles of a substance is independent of let me just if you have more moles, the temperature is going to increase more. If you have less moles, the temperature is going to increase less. I'm not 100% sure of that. I'm just throwing it out there. The SI unit, which is International System of Units, unit of specific heat is joules per Kelvin, so per mole. Like the specific heat measured, the molar heat capacity of a substance, especially a gas, may be significantly higher when the sample is allowed to expand as it is heated at constant pressure. So this is another problem. So we have to, if we can increase the temperature while keeping the pressure constant, then when it's heated in a closed vessel that prevents expansion, constant volume. And there's names for that. Well, I'm not going to get into that. The ratio between the two, however, is the same heat capacity ratio obtained from the corresponding specific heat capacity. This property is most relevant in chemistry when the amounts of substance are often specified in moles rather than by mass or volume. Molar heat capacity generally increases with molar mass, often varies with temperature and pressure, of course, and is different for each state of matter. For example, atmospheric pressure, isobaric molar heat capacity of water just above the melting point is a certain number. Its molar heat capacity is technically infinite because heat goes into changing its state rather than raising its temperature. I'm not going to get into change of state like liquid to gas and solid and all that right now. Let's see. Heat capacity per mole of atoms, or atom molar heat capacity, in which the heat capacity of the sample is divided by the number of moles of atoms instead of the moles of molecules. For example, the atom molar heat capacity of water is 1/3 of its molar heat capacity. This is more into thermodynamics, what I didn't do so good at. And yeah, so they're talking about, there is a formula. Molar heat capacity of a substance may be denoted by C sub m, is the heat capacity C of a sample of a substance divided by the amount of moles N of the substance in the sample, which also equals 1 over the number of moles, the limit of which the change in temperature approaches 0, times delta Q over delta T. Delta Q is the amount of heat needed to raise the temperature of the sample by delta T. Obviously, this parameter cannot be computed when N is not known or defined. Heat capacity, starting temperature. The heat capacity of an object, the molar heat capacity of a substance, may vary, sometimes substantially, depending on the starting temperature and pressure applied to it. Therefore, it should be considered a function of CMPT of those two variables. So there's a lot more going on here that meets the... Okay. I'll just check my stream here real quick. Okay. Where are we? Those parameters are usually specified when giving the molar heat capacity of a substance. For example, H2O is such 75 joule Kelvin moles at 25 degrees centigrade, 101.325 kilopascals. When not specified, published values of the molar heat capacity Cm generally are valid for standard conditions of temperature and pressure. Now, these standards have been very recently changed. I don't know exactly. I mean, I read something about it. So now it talks about units, energies measured here in calories. Molar heat capacity heat is joule per Kelvin per mole. Since an increment of temperature of 1 degree Celsius is the same as an increment of 1 Kelvin, that is the same as joule per degree Celsius per mole. In chemistry, heat amounts are still often measured in calories. Confusingly, 2 units with that name denoted cal or cal with a positive C, capital C, have been commonly used to measure amounts of heat. The small calorie, or gram calorie, is such a number. The grand calorie, etc., 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 etc. When heat is measured in these units, the unit of specific heat is usually such a number. Molar heat capacity, object, namely, blah, 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 consists of the SI unit of joule per Kelvin per mole is equivalent to kilogram meter squared per second squared per Kelvin. So the numbers that are used for measuring the volume are in English units. That would have to be converted if I wanted to calculate the energy in heat. Let me just read the rest of this stuff here. This is an interesting conversation. Temperature of a sample of substance reflects the average kinetic energy of its constituent particles, atoms or molecules, relative to its center of mass. Quantum mechanics predicts that at room temperature and ordinary pressure, an isolated atom in a gas cannot store any significant amount of energy except in the form of kinetic energy. Therefore, when a certain number of N atoms of a monoatomic gas receives an amount input of delta Q of heat energy in a container of fixed volume, the kinetic energy of each atom will increase by delta Q over N. Delta Q. See, they're using, I'm thinking, the way I'm reading this is I'm thinking the energy is taking into account something. The heat and pressure. So if the heat and pressure changes, the energy goes up at a certain rate. That's why I put all those cans out there. Okay, so each gas has a different specific, there's a number. You wait just a minute now. Let me just, rotational modes of diatomic molecule. Oh, they're really getting into some heavy duty stuff here. Because of these 2 extra degrees of freedom, the molar heat capacity of nitrogen is greater than that of a hypothetical monatomic gas by a factor of 5/3. Molar heat capacity C sub V comma M, volume and, wait a minute, sub M, constant, molar heat capacity at constant volume. C sub Vm, where is that? I was just reading. For nitrogen is 20.6 joule per Kelvin per mole, is greater than the hypothetical monatomic gas, which is 12.5 joules per hypothetical. Is that, what is that number? Molar heat capacity. Let me just try to scan down through here. Constant volume, specific heat capacity of a diatomic gas, is idealized. It's not linear here, according to this chart. As temperature increases, heat capacity goes from 3 over 2R, translation contribution only, to 5 over 2R, translation plus rotation, finally to a maximum of 7 over 2R, translation plus rotation plus vibration. So there's things happening within the diatomic gas at increasing temperatures. That's constant going specific heat capacity. Holy crap. Okay. Now I'm going to make an assumption that the temperature increase or changes in all of these gases is probably exactly the same. The rate of change would be the rate of change of temperature, which is delta T. Delta big T over delta small t. In the case of nitrogen, the rotational degrees of freedom are fully active already at minus 173 degrees C. Just 23 K above the boiling point. On the other hand, the vibration modes only start to become active around 77 degrees centigrade. Accordingly, the molar heat capacity is nearly constant at such and such joules per Kelvin per mole from 100 degrees Kelvin to about 300 degrees centigrade. At about that temperature, it starts to increase rapidly. Then it slows down again. They're talking about some serious temperatures here. 1500 degrees C. The molar heat capacity is such a number. At 1500 it's 36.9. 2500 it's 37.5. At 3500 the last value, okay, etc. The following table is a table of some constant pressure molar heat capacities of various diatomic gases at standard temperature. So they're saying standard temperature is 25 degrees C. At standard temperature, 500 degrees C and 5,000 degrees C, and the apparent number of degrees of freedom, etc., etc., etc. Alright, so there's chlorine, fluorine, hydrogen. I don't see nitrogen or oxygen and stuff here. But for hydrogen, it's from 200 degrees C to about 600, well, no, 2, 3, 4, from 300 degrees to 600. The change in energy, the change in molar heat capacity does not change. Now put that in your pipe and smoke it. I got too much gas in my room. I'm just coughing. Now they are actually, let's see. They are giving molar heat capacities for different temperatures at constant pressure. For 25 degrees and 500 degrees and 5,000 degrees. Now, my guess is no, it's talking about some other stuff here. Let me just see if I can figure something out here really quick. specific heat capacity of a substance times its molar mass. Okay, we're going to learn something here. Molar heat. We're not going to take into account the rotational or vibrational effects of the molecules as they are heated. We're going to make an assumption that the temperature is probably a linear. Okay, assumptions. My dad always told me never make assumptions. Well, we're going to make one. One is that the temperature increase is probably linear. Alright, so we've got molar heat capacity. I don't know what they use for a designation for that. Lost my bird. Molar heat capacity, something doing as heat capacity. Alright, C. They're using C. C sub M. Alright, so that would be C sub M equals the specific. We're going to use the specific heat capacity parentheses of gas divided by its molar mass. Now we know molecular weight. Molar mass is defined as the mass of a sample of that compound divided by the amount of substance in that sample measured in moles. Molar mass is defined as the mass of a substance divided by the amount of substance. So molar mass equals the number of moles. I think that's correct. Let me go back and look at that equation. Kilograms per mole. They're using grams per mole. Molecular weight is very commonly used as a synonym for molar mass. The mole was defined in such a way as that the molar mass of a compound, grams per mole, is numerically equal for all practical purposes to the average mass of one molecule in Daltons. Thus, for example, the average mass of a molecule of water is 18, etc. So we already talked about this, but for chemical elements without isolated molecules, such as carbon and metals, the molar mass is computed by dividing the number of moles of atoms. We're using gases. It must be understood that the 2019 redefinition of the SI base units concluded that the molar mass constant is not exactly 1 times 10 to the 3, but 0.99999999965, etc., etc., etc. Okay, so it's a little bit off. For all practical intents and purposes, it's 1 for now. Molar mass of atoms of an element is given by blah, 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 blah. Some elements are usually encountered as molecules, such as hydrogen, H2, sulfur, SH, chlorine, etc. The molar mass of molecules of these elements is the molar mass of the atoms multiplied by the number of atoms in each molecule. So we have the number of atoms in each molecule. For hydrogen, it's 2.01588 grams per mole. That's what? Molar mass. Shut up. Shut up. Shut it, bird. Molecular weight is an older term for what is now more correctly called the relative molar mass. This is a dimensionless quantity, a pure number without units, equal to the molar mass divided by the molar mass constant. Lovely. What is that? I have molecular weight. The mole and the relative atomic mass were originally defined in the International System of Units in such a way that the constant was exactly 1 grams per mole. That is the numerical value of the molar mass of an element in grams per mole of atoms was equal to its atomic mass relative to the atomic mass constant. Thus, for example, the average atomic mass of chlorine is approximately 34.446 daltons. On May 20th, 2019, this is very recent, well then it talks about that number. The molar mass constant is important in writing dimensionally correct equations. Formally, m is a times the molar mass constant. Oh. Which, for all intents and purposes, is 1. The molar mass has the units of mass per mole. Formally, m is a times the molar mass constant. Prior to that, okay, the molar mass constant is related to the mass of carbon-12 atom in grams. Hello. I'm not 100% sure where I'm going with all of this, but let's just continue reading this. The Avogadro Constant. We have to go into this because this is important. It's a proportionality factor that relates the number of constituent particles, usually molecules, atoms, or ions, in a sample with this amount of substance. Its SI unit is the reciprocal mole and is defined by such and such a number. That number is the number of particles that are contained in 1 mole. Hey! No. Effective 20 May 2019, it defined the Avogadro number as a value such and redefined the mole as the amount of substance under consideration that contains n constituent particles of the substance. Under the new definition, the mass of 1 mole of any substance, including hydrogen, carbon-12, and oxygen-16, is n times the average mass of one of its constituent particles. The physical quantity whose precise value has to be determined experimentally for each substance. pressure or is it gas constant? Oh, shot it. Shut it. Hello. I'm reading about SI definition. International System of Units, SI. That they're talking about determining the value for the Avogadro number. The Avogadro constant, Na, is related to other physical constants and properties. So you can relate, part of this whole conversation is being able to relate energy created in the form of heat to other energy reactions, I guess you could say. They're defining, it relates the molar gas constant R and the Boltzmann constant is related. Not that we need to get into that. They're talking about the Faraday constant and elementary charge. There's a question regarding, so you can create energy by the use of, well, energy, heat is energy. You can convert energy to, you can convert heat energy to electrical energy, and that relationship is maybe defined by the differences between the, well, here it talks about elementary charge in coulombs. They're talking about coulombs per mole, I think. No. Yeah, I think that's what that is. And it relates the molar mass constant m sub u and the atomic mass constant, currently such and such a number, and that is the molar mass constant, which is, for all intents and purposes, wait a minute. The atomic mass constant mu times the Avogadro constant is 1 times 10 to the 3 kilograms per mole. What? The molar mass constant, big M sub u, is equal to 1.6 times 10 to the minus 27 kilograms. That's confusing. I don't know what they're talking about. Some of this stuff in Wiki, I swear. Up yours. Up yours. Alright, let me go back to exactly where we were. We were talking about the ideal gas constant. What I'm trying to look for is a number that relates gas to standard temperature and pressure. And we're going to have to look this up here. It's good stuff. The Stone Temple Pilots. STP motor oil. I tried looking this up before and I couldn't do it. I put gas in here. Maybe that'll do it. Standard conditions for temperature and pressure. Now, I just read 25 degrees centigrade. NIST uses a temperature of 20 degrees and an absolute pressure of 1 atmosphere. We can relate that because they're they're talking about kilopascals here. The international standard metric conditions for natural gas are, we're not going to use that. That they're using 15 degrees centigrade. In industry and commerce, standard conditions for temperature and pressure are often necessary to define standard reference conditions, to express the volumes of gases and liquids and related quantities such as the volumetric flow. The volumes of gases vary significantly with room temperature and pressure. Standard cubic meters per second and normal cubic meters per second. This is important. Advertisements for equipment and machinery, etc., simply state standard conditions without specifying them, often substituting the term with the older normal conditions, NC. Good practice always incorporates the reference conditions of temperature and pressure. If not stated, some room environment conditions are supposed. And they're bringing humidity into this. We ain't got to worry about that. Now there are different standards listed here. EPA NIST, this is also called normal temperature and pressure, is stated at 20. 25 is something different here. I'm guessing 20 degrees. I think I wrote this down before. Because they're giving a value for kilopascals here. And we can relate to that, I guess. It gives us a relation, you know. So let me just write that down. So STP, standard temperature, pressure, which is generally a starting point for figuring things out, is okay, so since 1982, STP is defined at a certain temperature and an absolute pressure of exactly 100 kilopascals. STP should not be confused with the standard, etc. Standard state commonly used in thermodynamic evaluations of the Gibbs energy reaction. What is that? The Gibbs energy of a reaction. Maximum of reversible work that may be performed by a thermodynamic system at constant temperature and pressure. The Gibbs free energy, delta G equals delta blah blah blah, is the maximum amount of non-expansion work that can be extracted from a thermodynamically closed system. Can exchange heat and work with its surroundings, but not matter. The Gibbs energy symbol is also the thermodynamic potential that is minimized when a system reaches chemical equilibrium at constant temperature and pressure. Its derivative with respect to the reaction coordinate of the system vanishes at equilibrium point. Gibbs free energy, originally called the available energy. According to the second law of thermodynamics, for systems reacting at STP, there is a general natural tendency to achieve a minimum of the Gibbs free energy. I never studied this in, maybe, I don't believe I studied this in thermodynamics. One can think of delta G as the amount of free or useful energy available to do work. They're talking about processes, entropy. Because I think I read something about this, like a turbine or something. Maybe they use gas to make energy or something like that. I'm just curious here. Alright, back to normal. They're defining STP here as 0 degrees centigrade with an absolute pressure of 100 kilopascals. NIST uses 20 degrees centigrade and an absolute pressure of 101.325 kilopascals. They're calling that 1 atmosphere. 100,000 Pascal is 1 bar. The standard is also called NTP. Blah 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 blah. I sound like that person on Charlie Brown. Huh. Hi. Uh-oh, my website froze because there's so much here. What the hell did happen? Standard lab conditions. Molar volume of a gas. Stating the molar volume of a gas without indicating the reference conditions of temperature and pressure has very little meaning and can cause confusion. Molar volume of gases around STP and the atmospheric pressure can be calculated with an accuracy that is usually sufficient by using the ideal gas law. Why are they using 60 degrees Fahrenheit to obtain cubic feet per mole? Technical literature can be confusing because many authors fail to explain whether they are using the ideal gas constant R or the specific gas constant R sub S. The relationship between the two constants is, thus, where m is the molecular mass of the gas. U.S. standard atmosphere uses 8.31432 cubic meters pascals per mole Kelvin as the value of R. However, the USSA 1976 does not recognize this value, is not consistent with the values of the Avogadro Constant and the Boltzmann Constant. Holy. Really? So, my question is, if we're going to put a question here. If R is questioned, we have the ideal gas constant and we have the R sub S. That's the specific gas constant. And R sub S equals R divided by M, where M equals the molecular mass of the gas. Now, molecular mass is not the same as molecular weight. Now, let me look back in my notes. We have molecular mass, molecular weight of gases. V molar equals pound molecular weight. Molecular weight is expressed in pounds. Where did I write this down? I mean, molecular weight times gas. No, molecular weight times R. Gas molecular weight approximation. Why do I have MW times R? Shit. Let's look this up here. You know what I could have been doing? I could have been doing this research on the stream. In fact, why don't we set that up? We can set that up. I should have been doing that, and I was just here talking and stuff. So I want to look up. So look up molar mass. I should have been doing it on this computer. Where is this molar mass wiki? I can't do this, can I? Oh, the pain, Dr. Smith. Oh. All right. So we need to know what the molecular mass of gas is. So we got molar mass. And where was I reading this? Ideal. Molecular mass of a gas. Molecular mass of a given molecule is measured in Daltons. This is distinct but related to the molar mass. Now I can watch my stream here. Which is a measure of the average molecular mass of all the molecules in a sample, is usually a more appropriate measure when dealing with macroscopic weighable quantities. So that wouldn't be a gas. They're giving a value for the molar mass using conditions of known pressure and temperature. What the heck is that other number? P. That's pressure. N is the amount of substance, the vapor density. Oh, vapor density. Boy, oh boy, oh boy. The molar mass for hydrogen, for all intents and purposes, equals 1. I mean, they got 1.007 here. For normal samples from Earth with typical isotope composition, the atomic weight can be approximated by the standard atomic weight. I really love Google sometimes. Equal volumes of gases at the same temperature and pressure contain equal number of molecules. Molecular weight of a gas is equal to 22.4 times its density. That's important. I recognize that number. The volume of an ideal gas is thus, if we assume 1 mole of gas, then N equals 1, and this equation becomes thus, which is the second half of the equation for molecular weight. Why isn't this showing up here? What's wrong with this? Fuck. We can modify this law in terms of like molar mass. That's where molar mass, there's molar volume. We know that the number of moles equal to the mass divided by the molecular mass of the gas. Molecular mass of the gas. That's the number of moles. Yeah, that's like grams. If we plug the expression of number of mole in the expression into the expression of the gas law, we get this. No. No, this is not the answer. Yeah, no kidding. Tell me something I don't already know. There's something wrong with that site. Organic chemistry. One mole of gas occupies a volume of 22.4 liters at standard temperature and pressure. Make sure you thoroughly understand the following ideals. This is the law that says, if you go back to my lovely notes here. At any given temperature and pressure, 1 mole of a gas will occupy a fixed volume, regardless of the gas. So 1 mole of gas occupies a liter of 22.4 liters at STP. Okay, this is what I'm looking for. I think. Let's write it down on here. So 1 mole of gas equals 22.4 liters at STP, which here is defined as 1 atmosphere. which is, now that's not the accurate number. Where's that other list I have? Is it the ideal gas law? Where did I see that? Wait, I have 22.4. Aha. Okay, now we've got some more information. So that's actually, they're saying 103, but it's actually 101.325 kPa. So the V molar here also question mark VM equals 22.414 liters, or cubic decimeters per mole at 0 degrees C and 101.325 kPa. 0 degrees C. Okay, that's what was listed up there. What is this here? What are we looking at? Molar volume. And here we're looking at we're trying to find molecular weight here. It's not so easy. I thought I wrote something down, but I know I wrote the tables down. Like I have the molecular weights. Thermodynamics was not my forte, I'll tell you. I hated it. Total weight of the gas is the total volume by the specific volume. Yeah, there's something wrong with that. We're gonna get there. We're gonna find the answer to this. This is good stuff. Molecular weight is commonly used as a synonym for molar mass, particularly for molecular compounds. Molecular mass. Formula weight is a synonym of molar mass. I'm going crazy. Did I miss something? That is the molar mass of a chemical compound is numerically equal to its average molecular. The molar mass of a chemical compound was meant to be numerically equal to its average molecular mass. For the average mass of one molecule of water is about 18.0153 daltons, and 1 mole of water is about 18.0153 grams. However, while this equality can be assumed for almost all practical purposes, it is now only approximate. Well, when they talk about approximate, they're talking about doing experimentation for every. They're able to do this for every element that you're studying in your thermodynamic system. Um, you know, they're getting closer to the speed of light. Um, and this thing about Planck's constant, I believe that the Planck constant is incorrect. Cut it. Which is part of the study of the black body radiation. And if you look at the black body chart, there was another problem that was called the ultraviolet catastrophe. And you can see this chart's severely nonlinear at higher temperatures. So, using the Planck's constant to measure quantities of molecules and particles at high temperature is questionable. And so this chart here, this is classical theory, this black line, and there's some discussion about the ultraviolet catastrophe is the error at short wavelengths. So, depending on gases that are used or chemicals or whatever, when you look at them through the spectrometer to find out what their molecular mass and weights are and stuff like that, and then you plug them into maybe this formula here. This is the Rayleigh-Jeans law formula. Now, you ask yourself, well, what do all these formulas have to do with what we're studying? It has to do with constants that were discovered using experiments many, many moons ago. And some of the features to discover those constants have, for example, temperature is one of them. You have energy. I don't know. You've got H is the Planck's constant. K sub B is Boltzmann constant. The Planck's law does not suffer from ultraviolet and agrees well with experimental data, but its full significance, which ultimately led to quantum theory, was only appreciated several years later. They go into through some kind of theory here. It's pretty cool stuff. But it sort of relates to how constants are derived using experimental data and how they relate to temperature and pressure. For the purposes of the game mechanics of this particular game, it probably 99.9% doesn't matter. Um, oh, wait a minute. Okay, yeah. So the fact that I have all those different gases out there in those cans, and letting the temperature drop and fall, go to a cold temperature and back up to a high temperature over a long period of time, um, even though they're in a constant volume, they're going to have the same number of moles, but but with the temperature change is going to affect um, this part of these equations for what the heck was it? What was I looking at? The change in the energy of the substance is going to be different because the specific gas densities are different for each gas. So, in other words, if the temperature changes, it's going to change the molecular structure, the energy of that gas is going to change as the temperature changes. So, I mean, it just seems like I should be expecting different temperature numbers over a long period of time if they're using um, these formulas. I don't think they are. I just don't. So why even bother with this? Maybe it's to. I could be trying to look for something that's a little bit more realistic, and maybe I can incorporate that into the simulation. I used to do this when I was writing mods for Take on Mars. I did a resource mod, and I spent several months, like I spent 2 or 3 months at one time, and then 2 or 3 months later to finalize extracting resources out of minerals. But they didn't have this setup where you have the ability to mix gases and come up with certain equations to create energy. Like when you mixed the oxide and the volatiles, it's fine that the oxide has these different chemicals, like it's made of oxygen and nitrogen. So if you throw oxygen and nitrogen and hydrogen into the mix, you may have so now you're down to the basic elements again, and those elements are going to react. Um, and it's interesting how they threw oxygen, nitrogen, and hydrogen together to create a reaction that causes a lot of heat. Let's just look that up here. Well, the other thing is too. I mean, maybe the furnace provides a spark, but there's no electrical connection to that gas furnace. Heat treatment furnace, combustion. I mean, maybe there's something assumed. Oh, 24. They're talking about entropy and enthalpy, this heat energy and everything. High temperatures can start a fire. the heat of combustion is approximately uncatalyzed combustion in air requires relatively high temperatures. Complete combustion is stoichiometric concerning the fuel, where there is no remaining fuel and ideally no residual oxidant. Thermodynamically, the chemical equilibrium of combustion is overall on the side of the products, however. Blah, blah, blah. Now, see, here's something that I put in my mod for the other simulator. When you burn things in a furnace, then you get residue. So, like, you've got carbon monoxide, hydrogen, and you got unburnt products. You've got carbon monoxide, and that's something I actually haven't looked at yet. There is gases that get released from the certain ores that they're sticking into these furnaces. So this is another whole aspect, which I didn't got into, and they're actually using that. Like, for example, the carbon, okay? It just so happens, well, they're using Mars. Let's see. Mars soil composition wiki. There's a chart that I used right here. So this chart was the basis of my mod for Take on Mars, for setting up realistic resources on the planet. And let's see, like, for example, magnesium oxide is a constituent in the soil somewhere. So we take the magnesium and the oxide and we split it up, and then we use the magnesium as a component for making batteries. I don't know exactly what they use in the game to make batteries. Maybe they use gold, silver, whatever. This is a more, picking everything apart. What is actually the percentages of the chemical elements coming out of the various ores on Mars? And I did it took me 2 or 3 months to be able to figure out the minerals that are on Mars and where the constituents came from. One of the big ones was calcium. I think it was calcium oxide. There's a couple of terms, I can't remember the name of them, that had a lot of iron in them. And so I made up this company that takes the soils and the ores, and I fabricated. I said that these ores contained 100 times the actual element, but it kept the ratios of all of the elements the same. It's practically impossible to extract all of the elements on Mars needed to make things because the number of elements is just so small. There's a lot of iron on Mars, but how to get that iron into a usable quantity? So, iron has when you heat up iron, there's sulfur that occurs. That sulfur has to be removed, and I don't remember the process that I used. It's in my mod. That's actually kind of important because they're making steel. Now, unfortunately, steel is not the best product to use. there's an alloy. God, why am I getting into this conversation? Well, the creative mode in Stationeers is on Mars, so they have an alloy here that they're using called Invar. It's actually INVR. Wait. I don't know the correct spelling. Oh, it is Invar. No way, is it? It is. Oh, they're actually using this. Alright, so Invar is a nickel iron alloy. And what I did was I used this in preference to iron or steel because if iron has any sulfur in it, the cold temperatures on Mars will degrade it doesn't rust, but it just gets eaten up. So it degrades the quality. If you look at this, so there was another type of alloy that somebody's saying that we're using to get the most use out of the chemicals on Mars. I forget what it is, but I went with this. It's like a pig iron type of thing that you make, and then you take that pig iron, you mix it with nickel, and you come up with this alloy. So this has this this coefficient of thermal expansion. So if you use a certain percentage of nickel and alloy, you get I guess you get this dip here. So maybe it's approximately 40%. So I don't know if that's what I wrote down in my mod. I'll just write it down here. So Invar is 60% iron, 40% nickel. So that's 6, 4, or 3 iron and 2 nickel, 2 nickel. Now I can just check. I can check that later and see exactly what they're using for Invar. Now Invar is a better building material than steel. Where am I on my abnormalcy here? Right there. Oh, just throw that in there. Why I threw that in there, I don't know. Crazy, I guess. Heat of combustion. Alright, what are we talking about? The calorific value is the total energy released as heat when a substance undergoes complete combustion with oxygen. Okay, so oxygen is standard conditions. The chemical reaction is typically a hydrocarbon, which they are simulating, which is pretty cool, or other organic molecule reacting with oxygen to form carbon dioxide and water and release heat. This is energy per mole of fuel. There are 2 kinds of heat combustion called high and low heating value, etc., etc., etc. How much the products are allowed to cool and whether the compounds like H2O are allowed to condense. Kilojoules per mole. We're gonna We're getting into mixture of gases and everything else in this game. It's crazy. Alright. Heat of combustion is energy per mole. You get energy per mass of fuel, energy per volume of fuel. Energy per volume. So we've got energy per mole of fuel and energy per volume. So the reason why I wrote that down is so we can calculate the volume of the furnace and use that as a basis to go back and see if we can predict other heats of combustion for other chemicals, providing to see. They're probably not even using this. Combustion. Exothermic redox chemical reaction. High temperature exothermic redox chemical reaction. Between a fuel, the reluctant, and an oxidant, usually oxygen, that produces oxidized gas products and a mixture, etc., etc., etc. We are not going into, well, there's chemical mixture. There's basic chemical pressure, volume, temperature, mixture equations, but this gets into oxidation and reduction, and it gets into changes of the shells and the outer electrons and how many electrons are exchanged and the bonding and all kinds of stuff. Like here, this one, a redox couple is a reducing species and its corresponding oxidizing form, iron plus 2 divided by iron plus 3, which is plus 3. I think it has 2 spaces for electrons to. It has 2 extra electrons. Those are isotopes or something of that nature. I went through chemical equations to make batteries, to make, I used, see, they have waste products here. I used those waste products to create an organic solution that gave off it grew algae, and that algae created oxygen. They don't have that here. What's stoichiometric here? Let me just take a brief look here. The calculation of reactants and products in a chemical reaction. Well, that's fairly easy. That's just chemical balancing for the most part. Alright, methane is CH4. Which reminds me, methane, I don't think they're using methane in this program. Methane is, I believe there's methane on Mars. Methane is extremely, extremely valuable and important. When people go to Mars, there's going to be lots of carbon dioxide. There will be ways to make oxygen. That's not the problem. The actual problem on Mars is creating hydrogen. There is absolutely no way to come up with hydrogen in any chemical process. It has to be done using organic processes, and that's why I introduced in that mod for Mars. I introduced the alkali, the bacteria thing. I can't remember what the name of it is, but it eats up all of the waste products and it produces hydrogen. It's a plant matter that produces hydrogen. So I'm wondering about hydrogen in this game. There's water. We have there's no way to make it. There's just no way. The plants deal with carbon dioxide and oxygen. Hydrogen is your volatiles. It's used to make your materials. It produces other gases, carbon and so on. They don't have that incorporated here. So, let's see. So hydrogen is going, right now, according to the simulation in Stationeers, hydrogen is going to be a limited resource. No. What's the word I'm thinking? Well, it's a limited resource. The only resource that's reproducible is oxygen from the plants. Eventually, you'll run out of volatiles. You can't produce more from less. The only thing that can do that is organic matter. There's organic matter that produces different things. Well, your waste products, the waste products in the game, there's hydrogen. Let me look at that. I want to look at that while I'm thinking of it here. Wait, let me get the game going up here. Well, that doesn't help. So, I mean, we can look at this stuff and see if anything's changed. Whoa. Hydrogen is 19.9. Oxygen is 21.5. That's 21.6. 21.6, that's 20. Whatever the hell that is. Rocket fuel is 20.1. CO2 is 20.2, that's 21.1. 20.7. They're fairly close, but they are different.
Light
I mean, they're not
on.
different by a lot. Alright, Let's drop this waste can.
Waste tank critical.
So there's CO2 and oxygen in the waste. Why does hydrogen matter? Why does hydrogen matter? So, you make your base. You plant your plants. You're not really planning to leave. So you can exist, you can create whatever it is that you need to create with the volatiles that's available. You can take the gases from the different ores and stuff that you mix together and do whatever it is that you're going to make. You can make hydrogen that way. But it's once all of the hydrogen is made, then that's all you have. There's none left. There might be, like, you could recycle some things, and maybe in that recycling you may get some of the hydrogen back, but you're not going to get all of it back. I think the way they have it set up, in the not in the short term or the long term, but kind of in the midterm, you've got your base created, you've done everything you want to do, you've saved all your hydrogen, and maybe you've got enough stuff to build a rocket ship. But once you use the hydrogen for the fuel and you go into outer space, well, you'd better find some more hydrogen, or you're going to be pretty much, you're not going to make it. So when you build your ship, you are taking with you the constituents that you need to create hydrogen and oxygen and carbon, and go to your next location and set that all up and have your system going to make that stuff, because you may not find it somewhere else. And when you left Earth, you had all of the bacteria. The bacteria and stuff is a dried powder. It's like those brine shrimp that exist for thousands of years. And then you add water and poof, you've got little critters floating around. So for now, like, for all intents and purposes, it doesn't matter that we can't create hydrogen. But I think it's important to have to make an organic containment system. It's either like with the hydroponics. I mean, I don't know, because I haven't got that much into the game. There may be other plants that they have that produce something else besides oxygen. I don't know. It's something I haven't investigated. And the only thing is, if they, even still, you'd have to have a whole crap load of those plants, which is not a big deal because we can reproduce them. And that, I haven't gotten that far in the game yet. I haven't gone through and looked at all of the different plants, what they produce. We could actually just, I mean, not necessarily out of curiosity, but I really want to get into this molecular weight and get that problem solved, and I will too. But anyway, if I do, let's see, hydrogen, Stationeers. They probably won't talk about it that much. It says it comes from volatiles. Oh, look what they have here. Volatile type of gas can be used in combination with oxygen as a combustible fuel. In the form of ice, volatiles can be mined. Different ratios of volatiles and oxygen produce different temperatures and pressures during combustion. Combustion creates a large amount of heat, pressure, and CO2, which is interesting. The reaction is useful inside a furnace for smelting ores or creating alloys, but can be catastrophic when inside a canister or a room. It is labeled as in the atmospheric analyzer as H2, but it is not hydrogen. When burned, it produces heat, pollutants, and carbon dioxide in the following reaction. The reaction is inconsistent with volatiles being simple hydrocarbons. Too much CO2 is produced. But it may be consistent with more complex organic molecules. The reaction appears to only take place with specific quantities of gas. So oxygen is often left over even when there is an excess of volatiles. Volatiles plus oxygen, you get that from oxide, releases 3x and 6 CO2 and heat. So they're saying that the hydrogen is completely burned. That's the reluctant, as it's called. Oh, 2 volatiles. Wait. What's this? Yeah, I can't get to it. Oh, look what they have here that I almost missed. Volatiles have a specific heat of 20.4 joules per mole. Where did they get this information? Specific heat. See, I want to find that information to see how close they are to the realistic part of the game itself. Let's see. Maybe we can find something here. Specific heat's the amount of gas required to change the temperature of a mass of a substance by 1 degree. I was talking about this earlier. There's 2 types. Constant pressure, constant volume. Specific heats, Cp and C sub V, will vary with temperature. So the number they're talking about is 20.4 joules per mole. This is in not specific pressure, specific heat. Kilojoules per kilojoule Kelvin. The values above apply to undissociated states at high temperatures above 1500 K. Dissociation becomes appreciable and pressure is a significant variable. Pressure. The temperature when I mixed 3 oxide, and 1 volatile, the temperature popped up to about 1,300 degrees Kelvin. Wait, what this say? Oxide. It doesn't. Assuming that they're using the same temperature, the specific heat value for oxygen is around 1.3. But the temperature that we got in the furnace was only 1,300 degrees. There's a bit of a discrepancy there. Nitrogen is not considered to be a combustible substance when oxygen is the oxidant. Small amounts of various nitrogen oxides, commonly designated as NO, form when the air is the oxidative. See, there's things here like if you have higher temperatures and stuff like that, you're going to get more of a certain product. They won't have that in there. But the fact that they're actually using some of this information, it's interesting. So, spontaneous combustion is a type of combustion which occurs by self-heating. Increase in temperature due to exothermic internal reactions. So, the simulator is using exothermic reaction. And another thing, hydrogen is not the best way. It's not the best way to store hydrogen. If you make methane is a better way to store hydrogen because 1 mole of methane uses 4 moles of hydrogen. I wonder if you can mix methane and they don't have it in the game. Exothermic processes result in increase of the temperature. Yeah, I know that. So whatever we put in that furnace, well, they're using ice and, well, I don't know. Like, you can mix other gases in there, but I think oxygen has to be in there. Oxygen is what makes the fuel. And oxygen doesn't come by very easily either. You'd have to have a crap load of plants. I mean, it's just a freaking crap load. I'm still not going to get the answer I'm looking for. The above fact allows us to relate the measurable property of the density of a gas to its molar mass. Aha. Substituting these values into hang on just a second here. See, part of what I need to do in the game in order to predict things is to calculate constants. So in order to do that, this is good information here. So if we have PV equals nRT, let's go back to this again. PV equals nRT at STP of 273. Oh, am I in the right? I'm on the wrong. I'm on the wrong page here. Now, where did I write down STP? I probably didn't. Okay, I wrote it down right here. PV equals nRT. So this value R is questionable. R is questionable. For P equal to 1, N equal to 1, R equal to 1545 divided by, so question mark 1545 depends on gas divided by molecular weight of the gas is equivalent to a number. Where did I write that down? Eight point three one four. 8.314. The temperature they have as in Kelvin, T equals 273.15 degrees Kelvin. So let's see if we can, let's see what the calculator says here. So if we take 1 times 8.314, that's the theoretical value of R in the ideal gas law, times 273.15. And we divide that by, 1. No, something's wrong there. Something's wrong. Something's wrong. Charles' law. Boyle's law. Temperature, pressure, divided by, that doesn't work. Oh, we've discovered the density at standard temperature and pressure. That would be the specific density. That would be the density at standard temperature and pressure. Combine the molar mass and molar volume in such a way as to make the units come out correctly. Molecular weight. Well, I have that information. Somewhere. I thought I had two charts. What the hell? I had two charts here. Grams per liter. Molecular weight. Grams per mole. I wrote this. Wait, give me just a second here. This is. Shut it, bird. What did I write down? One mole of gas is 22.4 liters at that pressure. How come I can't come up with that answer? There was another chart. Molar mass, kilograms per mole, SI unit. Kilograms per mole. Hydrogen is 1. I thought there was a chart somewhere. For water, has a molar mass of 18 grams per mole. I have molecular masses ranging between 18. Oh boy. CH4 molecular mass. See, wait a second here. What's this? Yeah, this is just stuff. The molecular weight, or rather the molecular mass, is very close to the standard atomic weight. I hear they're making it equivalent. Grams per mole. Molar mass. Huh. Grams per mole. That would be... Oh, so if I use... So I'm getting into some... Wait just a second. I'm getting into something else. I'm like doing a couple of things at once here. It's crazy. Alright. Specific density of a gas at STP. That's 0 degrees C or 273.15 degrees K. And I think we're getting there. It's just taking unusually long. What are you doing? Look at this shit here. The fuck? And 101.325 kPa. So D sub G equals the molecular weight. No, the molar mass. Wait a second. The molecular weight. Oh, it's 2 times that number. Oh, they're using 2. Molecular weight. Molecular weight is equivalent to molar mass. Well, it says that here. You want to get fired? You're fired. You're fired. You're supposed to tell me this 2 hours ago. Let me make a note here somewhere in big letters. Where is... There was something else. I thought I was getting into molar mass, but... Alright. Where am I writing this shit down? Let's do it. We got molar volume. Okay. MW molecular weight is equivalent to molar mass MM. So this is going to be MW divided by I have to keep flipping back here. 22.414 VM, which is 22.414 grams per mole. So when you divide that out, the answer is going to be in grams per liter. That's the density. So the density of hydrogen equals 1.008 divided by 22.414. Divided by 22.414. That number is 0. It says 0.0450 grams per liter. So now we know how to calculate the specific density at STP for any of the gases. Why is that important? Because we are trying to calculate the volume of the equipment that we're using in the game. By knowing that volume, we can go back and predict what the temperature and the pressures are going to be, or we can predict what the temperature is going to be at a certain pressure for a certain gas, maybe. Or we're just trying to verify the system. How is the system working? And there's another number here. There's this number R. And I was doing specific heat capacity divided by the molar mass. Wait, that says number of moles. Molar mass is a number. Oh. That's not molar mass. This wiki is crazy. I don't know. What is that? Molar heat capacity. When I get rolling on something, I get rolling. the molar heat capacity may be significantly higher when the sample is allowed to expand as it is heated. High constant pressure than when it is heated in a closed vessel that prevents expansion. At constant volume. We are using constant volume delta Q is the amount of heat needed to raise the temperature of a sample by delta T. As delta T approaches 0. It's change in temperature. Huh. Good. Molar heat capacity. Holy mackerel. I think this is probably more than what the game is doing. Specific heat is joule per Kelvin per mole. That would cancel moles and give a specific heat capacity of joules per Kelvin. The theory predicts that molar heat capacity at constant volume, which is what we're having, of all monatomic gas will be the same, specifically 3 over 2 times R, where R is the ideal gas constant. So if we knew the value of, why is it doing that? If we knew the value, what the hell? If we knew the value of the molar heat capacity, then we can find out what the value of R is. It's supposed to be a certain number. Experimental values of noble gases. Those are noble gases. At 1 atmosphere and 25 degrees are all 12.5, which is 3 over 2 divided by R, even though their atomic weights range from 4 to 131. Those are monoatomic gases. This is that curve that we were talking about earlier. that's constant pressure. They're using standard temperature 25 degrees here. Alright, fine. That's carbon monoxide. There's nitrogen, hydrogen in there. Let's see. Constant pressure. Cm of hydrogen. Cm equals 28.9. That's actually H2. Joules per Kelvin mole. Cm of nitrogen is 29.1. And we know the number of moles. So the specific heat capacity, delta Q, specific heat wait, that's of 1 mole is going to be the same as the molar heat capacity. At 1 mole, I guess. That's Cm. But it's not helping me with something. I don't even know why I went there. I've got specific heat capacity. I've got specific density. What am I looking for? Lovely. Aha! Create a relatively simple method for determining molecular mass of a volatile substance. We'll use a modified version to determine the molecular mass of an unknown liquid. The density of gas is given by thus, where the molecular mass of the gas. Solving for the molecular mass, we get this number. M is the molecular weight. Molecular mass. Molecular mass is the same as the molecular weight, though. Oops, what's this? It's crazy. Density grams per milliliter. It also equals PM over RT. That has to be important. DG equals P. M is the molecular. What is M? It's the molecular weight. Divided by RT. So if we know the molecular weight, we know the standard pressure, the standard temperature, and we know R, we should be able to figure out the density of hydrogen. You would think. Let's see if it works out. So we've got 1, 0, 1, 3, 2, 6, 5, oops. That's in pascals. Times 1 point. That number is off by a factor of 1,000. So P is in kilopascals. So 101.325 times the molecular weight 1.008 equals divided by 8.314 equals divided by 273.15 equals. Hot damn, there it is. So what we've done here is we verified the specific density of hydrogen using the ideal gas law versus using the formula molecular weight divided by the molecular volume, which is 22.414 liters per mole. That volume number was not included in this calculation. So now we have a means of calculating the specific density, and we can take that specific density and the volume, multiply it together, and we can come up with the molecular weights of the total of the gases that are in there. So P is in KPA. So, that's cool. That's fucking cool. We fucking did something. Now, we can say, we can take the specific value for the gas, which is a known quantity at STP. This is all at STP. At STP must convert degrees C degrees Kelvin. I love this job. Alright, so what we're going to do, since dg equals molecular weight divided by Vm, and dg equals P in kilopascals times molecular weight divided by RT, we now have molecular weight. Oh shit, you know what I'm doing? I'm canceling out molecular weight and substituting volume. I'm just proving the gas law. This is MW, so then I multiply that by V and bring that over here. Wait. Is that correct? Does molecular weight cancel? Molecular weights cancel. MW over VM. So that becomes 1 over Vm. So Vm is, so Vm equals RT divided by P. PV equals nRT. Yeah, I just proved the ideal gas law for standard temperature and pressure using specific density. Specific density at 22. But we see, the question is, we don't know the volume. And R is going to be what it is. R is going to be what it is. So then volume is nRT. R is 8.314. T is degrees Kelvin. P is in kilopascals. And is the number of moles. And V is in liters. V must be in liters. V is in liters. Now, liters to cubic feet. Is there a conversion for that? Okay, 1 liter equals that. Wait, I think I want to convert. Yeah, that's correct. I think. So we're going to have a number of liters. We have to convert that to cubic feet. One liter equals 0.035 3147 cubic feet. Now, if we do cubic feet to cubic inches, and there's that number that we used before. 1 cubic foot equals 1,728 cubic inches. So now the only problem that we have is we have to have a pressure, a standard pressure and a standard temperature. And these are the numbers that I've been looking for. That's going to be our laboratory. So T is going to equal 0 degrees C. Wait, what? Uh-huh. Standard temperature is 0 degrees. Oh, that's a plus number. Okay. Lab conditions. 0 degrees C or 273.15 degrees Kelvin. Pressure is I'm going to make supper pretty quick. Convert pressure. Shit. Standard pressure. Here it says 101.325. What the fuck? $101.325. It's 325, not 315. I used 315 in that calculation. What the fuck? I used 315. Where'd they come up with 325? Surface temperatures. Megapascals. D. The fuck? Why? Why? That number is not accurate. It's 2.016. Jesus Christ. I just wrote this information down. Damn it. Let me just go through this calculation again because something's screwy. 101.325 times 1.008 equals divided by 8.314 divided by 273. Where the hell is the other calculation? It's the same number. 97444. Ah, it's a different number. So it's 325. That number was incorrect. I just put a 2 here. Alright. Pressure is 101.325. KPA. Yeah. KPA. So we have that. Standard temperature, standard pressure. So now we can calculate volume. nRT times P. So when we go to the tanks here, if I can find the damn things. We'll do, let's see, let's do oxygen. Oh wait, we don't know what we can't do the formula because it has to be at 0 degrees and 100 kilopascals. In order to calculate the volume, because we don't know what the relationship is. So, we now know how to calculate the volume. I went through a lot of rigmarole to do this. But I needed something. I mean, I needed quantifiable information. So I could use either formula. No, I can't because I don't know the volume. And I don't know the density. I don't know the density. We have to, when we calculate this, we're going to know the pressure, the molecular weight, the number R, and the temperature, and the number of moles. Well, for 1 mole. Now wait a minute though. Wait just a minute. What am I thinking? I've got pressure. I can set temperature, I can set pressure. What am I doing wrong though? Something's missing. How the hell am I gonna get 1 mole of oxygen? It doesn't matter because the molecular weight, or, well, wait just a minute. We know the density. We know the density. So what we do is we take the molecular weight. So then we've got to go back. Wait a minute here. So V equals the molecular weight. Wait a minute, what the hell? What is wrong with this picture? Oh. Am I going to be able to even determine the volume? Because the volume's going to be 22.414. What the hell is fucking going on here? Fuck, what time is it? 8 o'clock. I've been at this for 4 freaking hours trying to figure this out. It's made me hungry, I'll tell you that. I wonder what determines the number of moles. There's still something wrong. How the hell did I calculate that volume before? I used 10 moles times that times 293 divided by 200,000. Oh, I did this calculation wrong. Why is the volume always the same? Doesn't make any sense. So if I use the information that's available, the current pressure and the current temperature and the number of moles, it gives me the volume of the gas, but it doesn't give me the volume of the cylinder. The only way to get that information is I have to be at standard temperature and pressure, I think. I think that's what's happening. It's saying that the volume is changing, but how can the volume change? It doesn't make any sense. I'm trying to calculate the volume. The volume's always going to be the same. Oh, so the question is the volume going to be the same? So if I use those numbers, it's going to give me a volume. But I've seen pressure. The pressure can be lower than that, and the temperature can still be the same. That's going to change the volume. I don't know. I've done this for 4 hours and I just don't know about the volume in the freaking tanks. Because all these numbers, temperature, pressure, the R number, the molecular weight, they give a density. That density changes. So at the standard temperature, then it's going to be 22.4 liters. That's crazy. I don't know. I just don't freaking know. I can't figure it out now. I'm baffled. All I know is I probably can't figure it out because I'm hungry, so I'm gonna take a break and come back later and try to figure it out.